పెళ్ళైన 17 సంవత్సరాలు అవుతుంది. మాకు ఒక బాబు పుట్టిన ప్రస్తుతం.
A very good morning, friends. Today we will discuss about an important LAQ, that is long answer question in university examination, that is liver function test. We will discuss this with one easy mnemonic, that is A, B, C, D, E, F, G, H and I. This is a mnemonic to remember different liver function tests. For example, from A, it is albumin, serum albumin level and albumin globulin ratio. Then ammonia level, and third one is the alpha 1 antitrypsin. So this is from A. These are the functions tests, or these are the tests to assess the functioning capacity of liver. First we will discuss the mnemonic to remember the LFTs. Then we will see for the indications and different classification of different liver function tests. B for bilirubin, which includes total, direct and indirect bilirubin. Then bile pigments in urine, bile salt. From C, it is serum cholesterol level, then coagulation profile, which includes prothrombin time, then ceruloplasmin level. Then from D, it is dye, that is bromo sulphthalene. This is the dye which is used to assess the excretory function of liver. Then enzyme markers, different enzyme markers, which includes two types. The first enzyme marker is to assess the hepatic function, and second to indicate the obstruction, or to indicate the obstructive pathology or cholestasis. Enzyme markers includes SGOT, serum glutamate oxaloacetate transaminase, SGPT, it is also known as OTPT or AST and ALT. Then obstructive enzymes are alkaline phosphatase, gamma glutamate transferase and 5-prime-nucleotidase. These are the enzymatic markers. Then LDH1 is also important. Sorry, LDH4 and 5, it is important in assessment of liver function. Then F for serum ferritin level and also for fetoprotein. that is alpha fetoprotein AFP. Then G for globulin, serum globulins, and galactose tolerance test. Then H for hippuric acid excretion test. Then haptoglobin, etc. And I for immunological test. This H also include HBsAg, that is surface antigen or Australia antigen for detection of hepatitis B virus infection, and I for immunological test. That includes the test against the different viruses in viral hepatitis. So these are the different tests which are used to assess the functioning capacity of liver. You can take a snapshot here. We'll discuss one by one. Then we'll discuss the different functions of liver, indications of liver function test, and classification of liver function test. This is a simple mnemonic to remember the liver function test. So A, B, C, D, E, F, G, H, and I. These are the different tests which are used to assess the functioning capacity of liver. Now, one by one, albumin, serum albumin, globulin, and Ag ratio. These are the serum proteins and these are the serum parameters which are used to assess the functioning capacity of liver. Albumin, it is synthesized by the liver and it has half-life around 20 days and it indicates the chronic liver damage. It indicates the chronic liver damage because of its long half-life, that is 20 days. Then albumin, normal range of serum albumin, it is 3.5 to 5 gram per deciliter. The albumin level decreases in severe liver damage because it is synthesized by the liver. Also, this Ag ratio, it is important. Ag ratio means albumin globulin ratio. It is reversed in case of liver damage. It get reversed or it get altered. The normal is 1.5 to 2 is to 1. It get reversed in the liver damage and also in renal damage. So this is also important. It is also important to differentiate between true or false increase or decrease in the serum protein levels, Ag ratio. So this is all about the albumin. Then ammonia level, it is important in hepatic encephalopathy or in cirrhosis of liver or in urea cycle disorders. So these are the different conditions in which ammonia level get altered. The first one is the hepatic encephalopathy. Hepatic encephalopathy. Cirrhosis of liver and urea cycle disorders. In this disorder, ammonia level increases. Then alpha-1 antitrypsin, the deficiency of alpha-1 antitrypsin, the disease in which there is alpha-1 antitrypsin deficiency, liver is affected. It mainly affects the lung, but in chronic cases, it leads to the cirrhosis of liver. So these are the different parameters from A, albumin, ammonia, and alpha-1 antitrypsin. Coming to the B, that is bilirubin level, and it is important as most common indication for liver function test is the jaundice, and we have to differentiate between three types of jaundice, that is pre-hepatic, hepatic, and post-hepatic, also known as hemolytic, hepatic, and obstructive jaundice. Now coming to the bilirubin level, the total bilirubin, the normal range is up to 1.2 milligram per dl. Then conjugated or direct bilirubin, which is water soluble, the range is 0.2 to 0.4 milligram per dl. Indirect or unconjugated bilirubin, it is 0.2 to 0.6 or 0. Some book it is mentioned 0.7 milligram per dl. So these are the normal range. whenever there is hemolytic jaundice means yellowish discoloration of skin and sclera. In hemolytic jaundice, due to the breakdown of RBC, there is breakdown of heme into bilirubin, and unconjugated fraction means indirect bilirubin increases. There is increase in indirect bilirubin in hemolytic jaundice. In hepatic, both component increases. There is increase in both indirect as well as direct component. So that's why it is known as biphasic Vandenberg reaction. And in obstructive jaundice or obstructive pathology, due to the different causes, there is increase in the direct fraction or conjugated fraction. So it is detected by the diazo reaction. The bilirubin combines with the diazotized sulfanylic urobilinogen. It is absent in obstructive jaundice. So these are the different parameters from the B: bile, bilirubin, total, direct, indirect, bile pigment, bile salt, and urinary urobilinogen. That indicates are that used to differentiate between three types of jaundice. Now coming to the C, that includes cholesterol, coagulation profile, and ceruloplasmin level. So serum cholesterol level. So cholesterol synthesis decreases when there is damage, chronic damage to the liver. Our entire hepatocyte replaced by the fiber in cirrhosis of liver. Normal level is less than 200 milligram per deciliter. It indicates the synthetic function of liver, also metabolic function of liver. Then coagulation profile replaced by the fiber in cirrhosis of liver. Normal level is less than 200 milligram. Ceruloplasmin level. So serum cholesterol level. So cholesterol synthesis decreases when there is damage, chronic damage to the liver. Our entire hepatocytes are replaced by the fiber in cirrhosis of liver. Normal level is less than 200 milligram per deciliter. It indicates the synthetic function of liver, also metabolic function of liver. Then coagulation profile, that includes prothrombin time, mainly the prothrombin time. Prothrombin, it is a short-term marker of liver damage, and prothrombin time increases in liver damage because the clotting factors, they are synthesized in the liver. The half-life of prothrombin is 6 hours. So it indicates the recent damage to the liver, or it indicates the acute liver injury, prothrombin time. And third one is the ceruloplasmin. Ceruloplasmin level decreases in Wilson's disease. It is Wilson's disease. Wilson's disease is cerebro-hepatolenticular degeneration. There is KF3 in the cornea, and ceruloplasmin level decreases. So this is from the C. From D, there is dye test, that is BSP, that is bromosulfonane excretion test. It indicates the excretory function of the liver. It indicates the excretory function. This dye is injected through the IV line, and retention of bromosulfonane is measured by measuring the serum bromosulfonane level, by measuring the serum BSP level, that is bromosulfonane level. After 45 minutes, less than 5% retained by the liver in the normal cases. But in liver damage, the retention of BSP increases. Retention increases in the liver damage. So this is from the D. Then enzyme markers, it is important parameter of the assessment of liver disease. Enzyme markers, it includes hepatocellular damage, means liver specific enzymes E for enzyme markers. So for liver damage or liver diseases, it includes SGOT, serum glutamate oxaloacetate transaminase, or AST, aspartate transaminase. Normal level is 5 to 40 international unit per liter. Then SGPT is more specific than SGOT for liver disease. Another name is alanine transaminase. Normal level is 5 to 35 international unit per liter. This indicates if there is more increase in the SGOT, it increases the alcoholic liver damage and also cirrhosis of liver. There is increased AST-ALT ratio in alcoholic liver damage and cirrhosis of liver, also in myocardial infarction. SGPT is more specific for liver. It mainly increases in infective hepatitis. That is viral infection. So these two are important against LDH, lactate dehydrogenase 4 and 5. It is important in diagnosis of liver damage. LDH1 is for heart, that is myocardial infarction. These are the plasma non-specific enzymes. OTPT, plasma non-specific enzymes. Their concentration but whenever there is necrosis, proliferation, damage, or neoplasm of the cell, the concentration of this enzyme in the blood increases. That's why they are known as plasma non-specific enzymes. Now, second group of enzyme markers, they includes the obstructive pathology. They are cholestasis, diagnosis of cholestasis or obstructive jaundice or obstructive pathology. So it includes alkaline phosphatase. It is important because it is a ectoenzyme present on the cell surface of biliary canaliculi or biliary epithelium. And when there is regurgitation of biliary epithelium or biliary canaliculi, it causes release of ALP into the bloodstream. So ALP level in the bloodstream increases. In hepatic diseases, ALP level is only 2 to 3 times of the normal. But in cholestasis or obstructive pathology, it is 10 to 12 times of the normal. While in cancer, it is up to 25 times. So ALP level increases up to 10 to 12 times of the normal in the obstructive pathology. If another markers are gamma glutamine transferase. This is specific for alcoholic liver disease. This is MCQ. DGT is done for assessment of alcoholic liver disease. And 5' nucleotidase is also a coenzyme. The concentration of 5' nucleotidase increases in cholestasis. So whenever there is hepatic injury, damage to the liver cells, the alkaline phosphatase level increases 2 to 3 times of the normal. But whenever there is obstructive pathology, alkaline phosphatase level increases 10 to 12 times of the normal. OTPT level or SGOT-HGPT level, it is up to 1000 times of the normal in the infective hepatitis. Viral infection, it is 1000 times of the normal. Up to 1000 times of the normal. So it is in 1000, 2000 or 3000 international unit per liter in infective hepatitis. While in cholestasis, there is only 2 to 3 times increase in the SGOT and HGPT. So these are the different serum markers or enzyme markers which are done for assessment of liver function. Now coming to the F, that is ferritin and phytoprotein level. So F, it indicates the ferritin, serum ferritin level. Ferritin, it indicates the storage of iron in the liver. So it decreases, ferritin level decreases in anemia. And it is increases in hemocytosis, hemochromatosis, there is increase in the ferritin level. And second one is the alpha fetoprotein, that is fetoprotein. The concentration of alpha fetoprotein slightly increases in the cirrhosis of liver, but there is marked increase in alpha fetoprotein in liver cancer or liver metastasis. Maternal increase in AFP level indicates the neural tube defect. So this is from the F. Then G, it includes the globulin level. Globulins, that is alpha and beta globulins, they are synthesized by the liver, while gamma globulins, they are mainly by the plasma cells. The globulins normal level is 2 to 3 gram per dl. So there is increase in the gamma globulin in the chronic liver disorders. Then another is the galactose tolerance test. This stage, the globulin's normal level is 2 to 3 gram per dl. The globulin level so this is from the F. Then G, it includes the globulin level. Globulins, that is alpha and beta globulins, they are synthesized by the liver. By gamma globulins, they are mainly by the plasma cells. The globulin's normal level is 2 to 3 gram per dl. So there is increase in the gamma globulin in the chronic liver disorders. Then another is the galactose tolerance test. This test you use to assess the metabolic function of the liver. Metabolic function of the liver. Galactose is given and rate of galactose excretion is measured. It is generally utilized within a half to 1 hour. If there is retention of galactose, that indicates the damage to the liver function. Okay, it indicates the metabolic function of liver. Then from H, it is hepatitis surface HBsAg surface antigen for detection of infection by hepatitis B virus. Then haptoglobin level affected in the liver disorders. FGHR. Then immunoglobulins. They are done in cases of infections by hepatitis A virus, hepatitis B virus, hepatitis C virus, and so on. So these are the different tests which are used to assess the functioning capacity of the liver. Now coming to the short discussion of various functions of the liver and indications of liver function tests. So in short discussion of functions of the liver, the first one is the synthetic. So you know that synthetic parameter, that is albumin, then albumin, cholesterol, prothrombin, then triglyceride, lipoproteins, they are synthesized by the liver. Then second is the metabolic function. It is involved in the metabolism of carbohydrates, fat, and protein. In carbohydrate metabolism, it is involved in the glycolysis, it is involved in the glycogen metabolism. It is involved in gluconeogenesis. It is involved in regulation of blood glucose level. Then fat metabolism is responsible for fatty acid synthesis and oxidation. Then triglyceride synthesis of ketone bodies, cholesterol synthesis. In protein, it is important in catamine. A very good morning, friends. Today we will discuss about an important topic, that is plasma proteins. It includes mainly albumin, globulins, and fibrinogen. These globulins, they are again divided to alpha 1, alpha 2, beta, and gamma globulins. These proteins, they are classified on the basis of their electrophoretic mobility. Electrophoresis. This is a technique in which the charged particles moves toward the oppositely charged electrode. Negatively charged particles will move toward the positively charged electrode, and positively charged particles they will move toward the negatively charged electrode. This is known as electrophoresis. By this technique, we will separate this albumin, globulin, and fibrinogen. There are again 4 in globulins, that is alpha 1, alpha 2, beta, and gamma. So normal electrophoretic pattern, this is look like, if this is a positive electrode and this is negatively charged electrode.
Grammarly does more than catch errors. With Grammarly, you can find really good.
In normal pattern, it look like this pattern. Okay, this is a band of albumin followed by alpha 1, alpha 2, beta, and gamma. This is like it's a band of albumin, alpha 1, alpha 2, alpha 3, and gamma. Okay. So this is albumin. This is alpha 1 globulin. This is alpha 2. This one is the beta globulin. And this is gamma globulin. Okay. Albumin, alpha 1, alpha 2, beta, and gamma globulin. Their concentration, the albumin normal range or reference range is 3.5 to 5 gram per dl. Globulin, it is 2.5 to 3.5 gram per dl. Fibrinogen, it is 200 to 300 milligram per 100 ml of deciliter. Okay, this is the concentration. In globulins, the alpha 1 globulin, it is 0.3 to 0.5 gram per dl. Alpha 2, it is 0.4 to 0.8 gram per dl. Beta globulin, it is 0.6 to 1.1 gram per dl. And gamma globulin, it is 0.8 to 1.8 milligram per dl. Okay, this is respective concentration of albumin, globulins, then alpha 1, alpha 2, beta, and gamma globulins, and fibrinogen. You will get extra band or extra elevation in the gamma region when there is fibrinogen, or when we use plasma in place of serum, you will get additional band of fibrinogen, which can be confused with M band in multiple myeloma. Remember this, if you use plasma, you will get extra band of fibrinogen. Plasma, when you collect a blood in a tube which contains anticoagulant, then you will get a plasma. Plasma means it is serum plus clotting factors. Clotting factors. Okay, you can remember this: plasma present PP fibrinogen. In plasma there is fibrinogen. Serum, it is without clotting factor or without fibrinogen. Got it? If you use plasma, you will get an additional band or additional spike in the gamma region. It is due to the fibrinogen. Okay. Now we'll discuss one by one, that is albumin and different globulins. This alpha 1 globulin, it includes alpha 1 globulin, that is alpha 1 antitrypsin, then alpha 1 lipoprotein, that is HDL, okay, then orosomucoid, this is a protein, it belongs to alpha 1 globulin, then retinol binding protein or retinol binding globulin, retinol binding protein, then thyroxine binding globulin and cortisol binding globulin, or it is also known as transcortin. So alpha 1 globulin includes alpha 1 antitrypsin, alpha 1 lipoprotein, that is HDL, orosomucoid, retinol binding protein, thyroxine binding globulin, and cortisol binding globulin or cortisol binding protein. These are included in the alpha 1 fraction. Alpha 2, it includes this alpha 2, it includes alpha 2 macroglobulin, haptoglobin, prothrombin, ceruloplasmin, etc. So alpha 2 fraction includes alpha 2 macroglobulin, it also means alpha 2 microglobulin, haptoglobin, prothrombin, and ceruloplasmin. Then beta, it includes LDL, that is beta lipoprotein. Then it includes transferrin, it includes hemopexin, transferrin, LDL, they are included in the beta fraction. This gamma globulin, it includes globulins, immunoglobulins. The main immunoglobulins are IgG, IgA, IgM, IgD, and IgE. Okay. So these are the different plasma proteins, and this is the fractionation of plasma protein by electrophoresis. These are the different proteins which are included in alpha 1, alpha 2, beta, and gamma. Alpha 1, alpha 2, beta, and gamma. Okay. Now coming to the functions of these plasma proteins, the most important is this albumin. The albumin is important and most predominant protein. It is a simple protein. Rest of the proteins they are really glycoprotein, but this albumin is a simplest one. The four main functions of albumin it includes it is responsible for maintenance of colloidal pressure. First function. Second important function of albumin it is nutrition. Third one is the buffering action, and important one is the transport. So it is important in the transport of free fatty acid. Transport of free fatty acids is important in transport of steroids. It is important in transport of hormones. It is important in transport of ions. It is important in transport of bilirubin. So it is an important function of albumin. That is transport of various compounds. Free fatty acid, bilirubin, steroid, hormones, and ions. One protein we missed here in beta. That is plasminogen. In the beta globulin. Okay. So these are the important functions of albumin. Now coming to the alpha 1, that is alpha 1 antitrypsin is inhibitor of trypsin. Then lipoprotein HDL, all of you know the role of HDL. Yes, it is responsible for transport of cholesterol and phospholipid. Transport of cholesterol and phospholipid. It is responsible for reverse transport of cholesterol. Tissue. The next one is the retinal binding protein. It is in the transport of retinol. Thyroxine. It is mainly in the transport of thyroid hormones.
तो हमारे जो बच्चा है 7 मंथ का है, उसका नाम साबिर है, अभी वो एडमिट है यहाँ पर, उसको जो है लिवर ट्रांसप्लांट का बोले हैं सर ने, तो हमारे पास
it is in the transport of cortisol. These are the important functions of alpha 1 globulins. Now coming to alpha 2, that is alpha 2 macroglobulin. That is important function of alpha 2 macroglobulin is it is an anti-trypsin. It has anti-trypsin and anti-plasminogen activity. The macroglobulin it bonds with the heme and prevent the excretion of heme. Then prothrombin it is a clotting factor. Ceruloplasmin it is in the transport of copper, and it is also responsible for conversion of ferrous into ferric. Okay, so these are the alpha 2 globulins. Alpha 2 macroglobulin, anti-trypsin, anti-plasmin activity. Macroglobulin binds with the heme and prevents excretion of hemoglobin. Prothrombin, clotting factor. Ceruloplasmin it is responsible for transport of copper, and it also responsible for conversion of ferrous into ferric. Now the beta globulin, LDL, it is mainly in the transport of cholesterol from liver to peripheral tissue. This is known as bad cholesterol. Liver to peripheral tissue is responsible for it. Transferrin is in the transport of iron. Hemoptysin is in the transport of heme. Plasminogen it has adrenolytic activity. So these are the important functions of beta globulin. That is transport of heme, and plasminogen is converted into plasmin, and which has adrenolytic activity. Last one is the gamma action. It is a diffuse action, and it has 5 types: hemoglobin G, A, M, T, and E. The most predominant form in serum is IgG. Hemoglobin G it is predominant. It is a monomer. It causes placenta, and it is responsible for secondary immune response. This is all about IgG. Then second, IgA. It has 2 types: serum immunoglobulin and secretory immunoglobulin. It is found in various secretions, and it is a diamond. Then it is a M. It is a pentanoic molecule, millionaire molecule. It has highest molecular weight. It is second largest immunoglobulin. It is responsible for complement fixation by classical pathway, named by the IgG or by IgM. It is responsible for primary immune response. And in these 5 molecules, monomers they are connected by J chains. Also, the J chain is created immunoglobulin A. D. The exact function is not known immunoglobulin D, but it acts as a D cell receptor. Immunoglobulin D, and this is least concentration, and it is responsible for allergic response. Now this is all about. You can take a snapshot here. This is all about these plasma proteins. Now you see the abnormal pattern apart from the normal pattern in electrophoresis. There are A very good morning, friends. Today's topic of discussion is iron. It is a LAQ university exam, and you may get a case on iron deficiency. Iron is a trace element because requirement of iron is less than 100 milligram per day. Total iron content in body is 3 to 5 gram. Of these, 75% of iron it is present in hemoglobin. So iron is an important constituent of hemoglobin. Other proteins which contain iron, they are myoglobin, then cytochromes, then iron sulfur protein, cytochrome P450, some enzymes that includes catalase, peroxidase, xanthine oxidase, and tryptophan pyrolinase. So these are important compounds which contain iron. Now coming to the important functions of iron related to these compounds. As it is present in hemoglobin, the main role of iron in our body is to transport oxygen to the tissues. And carbon dioxide to the lung. This is the important function of iron in our body. Apart from that, in myoglobin, then cytochromes and iron sulfur proteins, they are involved in the cellular respiration, that means electron transport chain. Cytochrome P450 it is involved in the detoxification process. Catalase, peroxidase, they are important as an antioxidant. Xanthine oxidase is involved in the purine degradation. Tryptophan pyrolinase is important in tryptophan metabolism. So these are the important functions of iron in our body. Now coming to the RDA, recommended daily allowance of iron for adult males.
So I've got my essay written, and I've been working on it for about a week. So now I'm going to show you how I use Grammarly to edit. Okay, so here's my essay, and I'm going to click through Grammarly's.
It is 10 milligram. For menstruating female, it is 20 milligram, and it is 40 milligram in case of pregnancy and lactation. Demand also increases in growing children. It is near about 10 to 20 milligram per day. Coming to the sources of iron, the important source of iron is green leafy vegetables. Leafy vegetables, it contains near about 20 milligram per 100 gram. Then cereals and pulses it contains 10 milligram per 100 gram. Cereals, 5 milligram per 100 gram. Then jaggery, it is an important source of iron. Then liver and meat. Liver contains 5 milligram per 100, meat contains 2 milligram per 100 gram. These are the important sources of iron. Then it is also present in dry fruits, beetroot. Then milk is a poor source of iron. It contains 0.1 milligram per 100 ml of milk. So it is a poor source of iron. Now coming to the absorption, transport and storage of iron. Absorption, transport and storage. Iron present in food in the ferric form. It is converted into ferrous form. This ferrous form gets absorbed into an intestinal mucosal cell with the help of protein. The name of that protein is divalent metal iron transporter 1. With the help of this protein, iron get absorbed into the intestinal mucosal sac. And intestinal mucosal sac, this iron is converted into ferric form with the help of peroxidase. And it gets stored in the intestinal mucosal sac and transport and storage iron. Absorption, transport and storage. Iron present in food in the ferric form is converted into ferrous form. This ferrous form gets absorbed into an intestinal mucosal sac with the help of protein. The name of that protein is divalent metal iron transporter 1. With the help of this protein, iron gets absorbed into the intestinal mucosal sac. And intestinal mucosal sac, this iron is converted into ferric form with the help of peroxidase. And it gets stored in the intestinal mucosal sac as ferritin. It condenses with apoferritin, get converted into ferritin. Ferritin is a storage form of iron in the intestinal mucosal sac, liver, spleen, and bone marrow. Now this ferric form, with the help of ferroreductase, is converted into ferrous form and transported out of intestinal mucosal sac with the help of protein known as ferroportin. It is in the plasma now. In the plasma, this ferrous is converted into ferric form with the help of ceruloplasmin, which has peroxidase activity. Now this ferrous condenses with apotransferrin and it gets converted into transferrin, which is a transport form of iron in the blood or plasma. Now this transferrin, iron from this transferrin is utilized in the enzyme cytochrome P450, hemoglobin, myoglobin, and remaining part of iron gets stored in the liver, bone marrow, spleen in the form of ferritin. So this is a storage form of iron, and also hemosiderin. It is also a storage form of iron. The regulation of iron level is done at the level of this mucosa, that is known as mucosal block theory. Mucosal block theory. When demand increases, absorption increases, and demand decreases, absorption decreases, which is at the mucosal level. That's why it is known as mucosal block theory. And hepcidin, it is a protein which downregulates the level of divalent metal iron transporter and ferroportin. It is important in the regulation of iron at the mucosal level. Iron is known as one-way substance, one-way element or substance, because there is very less excretion of iron through the bile, sweat, and hair loss. Less than 1 milligram per day iron loss through the body. That's why it is or substance, because there is very less. It is a protein which downregulates the level of divalent metal iron transporter and ferroportin. The regulation of iron level is done at the level of this mucosa, that is known as mucosal block theory. Mucosal block theory. When demand increases, absorption increases, and demand decreases, absorption decreases, which is at the mucosal level. That's why it is known as mucosal block theory. And hepcidin, it is a protein which downregulates the level of divalent metal iron transporter and ferroportin. It is important in the regulation of iron at the mucosal level. Iron is known as one-way substance, one-way element or substance, because there is very less excretion of iron through the bile, sweat, and hair loss. Less than 1 milligram per day iron loss through the body. That's why it is known as one-way element. It is utilized and reutilized again and again. That's why it is known as one-way element. Now coming to the deficiency manifestations of iron or diseases which are related to the iron. The important disease and most common disease in developing country is the iron deficiency anemia. Iron deficiency anemia. Causes of iron deficiency anemia includes increased demand and decreased intake. Then chronic blood loss. As in ulcer or worm infection, there is chronic blood loss. Also, there is blood loss in post-partum period. So, increased demand, decreased intake, chronic blood loss, then lead that causes the iron deficiency anemia. The important cause of iron deficiency is repeated pregnancies. Symptoms include two important symptoms. The first one is the apathy. Apathy means sluggish and dull child. There is school performance, fatigue, weakness in the deficiency of iron. This is the first important symptom of iron deficiency. Second is the anemia. That is microcytic hypochromic anemia. These are the important manifestations of iron deficiency. There is atrophy of mucosal and gastric mucosa, that is known as achlorhydria, and also it is known as Plummer-Wilson syndrome. But these are the important manifestations of iron deficiency. Laboratory investigations include lab diagnosis, serum iron level, which decreases in the iron deficiency anemia. Second, total iron binding capacity, which is near about 400 microgram per deciliter. This is the iron binding capacity, means capacity of binding iron to the transferrin. The transferrin normal level is 250 milligram per deciliter. So TIBC level in the iron deficiency anemia increases. Then hemoglobin, this is the general protein investigation. In case of male, it is 14 to 16 gram per dl. In case of female, it is 13 to 15 gram per deciliter. So hemoglobin level decreases. In iron deficiency anemia, serum iron level decreases, TIBC increases, and hemoglobin level decreases. Two important diseases which are related to the iron, excess of iron. Manifestations of iron deficiency. There is atrophy of mucosal and gastric mucosa, that is known as achlorhydria, and also it is known as Plummer-Wilson syndrome. But these are the important manifestations of iron deficiency. Laboratory investigations include lab diagnosis, serum iron level, which decreases in the iron deficiency anemia. Second, total iron binding capacity, which is near about 400 microgram per deciliter. This is the iron binding capacity, means capacity of binding iron to the transferrin. The transferrin normal level is 250 milligram per deciliter. So TIBC level in the iron deficiency anemia increases. Then hemoglobin, this is the general routine investigation. In case of male, it is 14 to 16 gram per dl. In case of female, it is 13 to 15 gram per deciliter. So hemoglobin level decreases. In iron deficiency anemia, serum iron level decreases, TIBC increases, and hemoglobin level decreases. Two important diseases which are related to the iron excess of iron, that includes hemosiderosis and hemochromatosis. Hemosiderosis, here there is excess iron due to increased absorption of iron. It is typically found in Bantu tribes of South Africa. That's why it is known as Bantu siderosis. And second condition is hemochromatosis. In this condition, there is excess of iron and it gets deposited in skin, bone marrow, liver, spleen. Deposition under the skin, it gives yellow to brown coloration, and that is known as bronze coloration. Bronze coloration to the skin. The combination of hemochromatosis, diabetes, and cirrhosis of liver, diabetes mellitus, and hemochromatosis is known as bronze diabetes. Bronze diabetes. So this is all about the iron. Hope you understood the iron. Keep watching. Thank you.
గురుమునరత్లో
An essential mineral that our body needs to get through the diet is copper. And typically we take in about 1 to 2 milligrams per day from the food we eat, things like whole grains, beans, nuts, and potatoes. But really our body only needs about 0.5 milligrams per day. So copper is excreted. About 90% of the excess copper is excreted into the bile, where it eventually ends up as fecal copper. And the other 10% is excreted in the urine. In Wilson's disease, there's this genetic defect that results in the excess copper being kept in the body and deposited in various tissues, where it's definitely not supposed to be. And just like iron, free copper can react with hydrogen peroxide in the body to form the hydroxyl radical, a reactive oxygen species that's pretty good at damaging tissue. So over time, those tissues are seriously damaged by free radical generation. Now, your liver cells, or your hepatocytes, play a really important role in helping the body get rid of excess copper. So usually the copper from the diet is absorbed into the stomach and small intestine via enterocytes and passed off into the portal vein to the liver. Once it's in the liver, it's sent to a special transport protein called ATP7B, which has a couple super important jobs. The first job is that it binds copper to apoceruloplasmin, which is the major copper-carrying protein in the blood, and is responsible for carrying about 95% of the copper in the blood. After it binds copper, it's then just called ceruloplasmin, and this guy can haul 6 molecules of copper at once. ATP7B's other job is to gather up the rest of the copper into vesicles to be exocytosed into the bile caniculi, where it goes into the bile and is eventually excreted. With Wilson's disease, there's this autosomal recessive defect in the ATP7B transport protein. As you could probably guess, that means that it can't incorporate the copper into ceruloplasmin or excrete it into the bile. Since it's not doing either of these things anymore, the copper builds up inside the hepatocyte and starts to produce free radicals. Eventually, all this built up copper and free radical damage injures or destroys the hepatocyte, causing free copper to spill out into the interstitial space, and from there it can access the blood supply. Once it's in the blood supply, it's circulated to and deposited in other tissues, where it also causes free radical damage over time. One organ in particular is the brain, and for this reason, Wilson's disease can have serious neurological symptoms and complications. Depending on where it deposits, it can cause different disorders. If it deposits in the
until in a dinner itself.